Hello, everyone. Rob Persons with Artesyn Embedded Computing. Here again, presenting a non-Vita presentation. Jerry likes that because it's something always different for this group. What I'm going to be talking today about is looking at the securing of tactical systems. Primarily, these are going to be Navy-based systems using some concepts that we heard earlier from Dave at Curtiss-Wright and Nigel from Concurrent. And we're looking at specifically cybersecurity kind of issues that are potentially happening or could happen to some of these systems. Traditionally, tactical systems, you'll see, have been fairly open environments, typically because of either the hardware architectures that have been used or just the physical location where they are. They're in the middle of a ship, so it's kind of hard to get to these things. But there are increased concerns about it, and we'll talk a little bit about that today. So let's look at an evolution of what the typical Navy systems have been like, or just tactical systems in general. I'm using Navy because that's what we're most experienced with personally. So we'll use that as kind of a foundation for what a tactical system looks like. In the old days, they used these Yuck 43s from Honeywell that were proprietary closed environments. These were mill standard computers, had very limited amount of connections going into them. They were very purpose-built for whatever device that they were controlling. But over the years, we saw this transition into the commercial off-the-shelf. This happened in the 90s. The Navy were one of the major groups that were actually really trying to drive this whole concept of eliminating these proprietary, non-off-the-shelf sorts of architectures so they can get all the advantages of COTS, multiple vendors and all that sort of thing. VME bus was a transitional product and still is being used in many places. And you saw some increased interconnectivity either from the VME bus, and then eventually we started to see some increased network connectivity going into these systems. To today, where a lot of these high-end systems are network-centric types of devices. A bunch of servers in a backplane that are all talking some form of IP, either 10 gig, 40 gig, 1 gig, or it could even be InfiniBand or other architectures. Again, exposing potential access points into these tactical systems. So in the process of a typical system that would be used for a tactical program, what we see is a bunch of interconnecting communications through internal backplanes, but again, it's IP-based traffic that's happening between these devices through some centralized switches. Beyond that, we actually see those systems in turn in a shipboard perspective interconnecting to other systems, and it could be the same kind of system as we see here through top of rack switch, or it could be disjunct systems, radar systems, sonar, IR. There's a bunch of different systems that could be interconnecting into the main platform. Let's say it's in this case, I'm kind of representing an Aegis weapon system, which is a tactical control unit on an Aegis destroyer. And eventually there's also the need to move and share this data from remote locations. It could be other ships in the fleet, it could be aircraft, or it could be command control sorts of applications. In this typically the webs, the clouds that you see on the side are protected clouds, but there is an element of sharing that's happening here. Today, many of those external links are very carefully controlled and are secure communications paths. If it's talking to an aircraft, if it's talking to another ship, those are using well-defined communications protocols and codecs that are actually protecting that data to the warfighter. It could be a ground base. It could even be back to a command and control center. So we're not really talking about the links necessarily going away from the ship. What we're looking at is really the data that's happening within. So we have data that is, for all practical purposes, there's encryption starting to creep in, but a majority of the data that's moving really within these tactical systems themselves is unencrypted. So what we're talking about here is the potential of starting to add encryption localized within the machines themselves and actually really tie down how these systems are displaying information and utilizing information. Again, looking at the possible places where we can start to improve encryption in these individual tactical systems. The first place to look at is a top-of-rack switch. And sure enough, there are plenty of technologies out there today, off-the-shelf technologies from Cisco and others, that add that capability of taking inbound lanes of traffic, encrypting it, and then protecting it as it's communicating between independent points. The problem is you still have the individual machines themselves, which have integrated switches and could potentially give you access points into some critical information. So then the next thing you look at is, okay, well, what if we go and just actually start to protect the data that's flowing within the system through the switch itself? And that's a reasonable way of doing it. But in most of the switches that you see today in these kind of network-centric applications or systems, they're very low-performant sorts of processors in there. They're relatively, they're there to be able to manage a switch and really do not a whole lot more. So they're really not good candidates for this type of application. Eventually they may be, because we're seeing the processors that would be used for these, what we call service processor for these switches, will start to add some hardware capabilities for encryption, as you'll see in a moment. But what we're talking about is looking at potentially encrypting the data from the source. So the actual applications, the locations where the server blades are in there are actually doing the encryption themselves, and everything that's passing on the backplane or away from the system is encrypted all the way along the pipeline. So there's been an evolution of encryption algorithms over the years. This is just kind of a simple tutorial on what encryption is about. And we've heard references to it earlier, as I mentioned, from previous presentations. Again, the idea is you have data that's in some plain text form. It could be, computer data, or text. But the idea is you take that basic data that you want to share somewhere else. You use a key of some length, and you have an algorithm that actually turns that into indiscernible traffic that, if it was captured on its own along the path, can't be easily determined what it is. And the same path on the return side as well. So you get this encrypted data, and then it's decrypted into something that's usable. There's the concept of keys we mentioned. There's both private and public. Private keys really represent a key that is known and has to be secured before the application starts. And so all the elements inside the system, let's say each of the server blades would have a private key that would have been well known and burned into the application space. There's also the concept of an asymmetric key or a public key, where there's a combination. It's actually a combination of private and public. So you have your local private key that can be used along with the public key to be able to actually do that encryption and de-encryption. And these are mechanisms that have evolved over time and are very, very sophisticated, and actually these newer algorithms are very, very protective. We use them every day, right? So if you're doing any kind of financial transaction over the internet, you're using this technology today. And the other aspect of this is how you actually go through the encryption and from the perspective of the algorithm that's working it, how much data are you processing at a given time? There's two different methods. One is a block, which is kind of the general way it's done today. I don't think there's too many of these modern encryption methods that are actually using stream. The idea is you take a block of data, you apply the key to it and with the algorithm, and it scrambles a block of data, and then it pads the rest of it with the blank data at that point, essentially. One of the most well-known and one that the NSA really has approved for encryption is AES, or Advanced Encryption Standard 256. The 256 represents the key size, so it's a 256-bit key that's used for it. This is one that is actually probably the most prevalent out there that's moving classified information around through the network, and is becoming more and more important as time goes on. So this is a kind of an example of what an encryption algorithm would be. So if we look at this from the approach of encrypting data on a typical payload board that might be in one of these tactical systems, this is our 7540 that we just released. Traditionally, what you would see are algorithms that have been developed and running in the cores of the processors. And there are a number of protocols, for instance, AES 256, that would run inside a processor, and this is a logical approach to doing it. The disadvantage is some of these algorithms, especially the ones with the more complex ones with the very large key sizes, they can take up a lot of processor cores just to do that encryption. And so there's always been this kind of element to where we don't want to give up on the performance of the processor board just to be able to do encryption, though there's a necessity to actually potentially add that kind of capability. You can go along and actually start to add multiple instances of these encryption engines to be able to help potentially encrypting one side, decrypting the other side, and actually take up, but the problem is it's a trade-off. How much of the resource that you want to use for actually doing the real application do you want to give up to do the encryption? So what we've seen has been a trend towards hardware acceleration of doing encryption and decryption. Intel actually has something that they've developed probably back, let's say 8 years ago. I think it was like 2002 when they had first instances of this. It's something called Intel Quick Assist. Quick Assist technology is actually a hardware coprocessor that you can use. Typically, it was using it in parallel to the processor to be able to offload some of the functional things that you need to do for encryption, and in this case, compression, decompression, but have it be done in hardware as opposed to doing through a software algorithm that you might run in your processor. You can see you can actually see below here some of the algorithms here, and these are all really the most prevalent ones that are of interest today for doing cryptography. It handles a variety of different key functions, and you can see the compression, decompression. Traditionally, these devices have been, again, coprocessors. So they're not built into the processor. They're not built directly into something that could be closely associated with the processor. So we struggled as a company to find enough real estate on these boards to be able to add this capability. When the boards were a little bit less complex, we were able to put it directly on the main board itself. But because of how much real estate's taken up with these new processors, memory, and all that, we had to migrate it off to an RTM. In the case of advanced TCA, this is a real transition module for it, which was okay, but it added expense. You see, you have to have a PCI Express bridge there. You have a couple of devices, and you have to use an RTM. If you didn't want to use an RTM, you're really kind of stuck on how you could do encryption. But what's happened recently with the advent of the Xenon Gold processors, so the Skylake SKUs of Intel's Xenon processors, this functionality of Quick Assist has actually been able to migrate directly into the PCH. So the host bridge that you develop, that you need to use for developing a base design, now has the capability of doing Quick Assist directly inside the PCH itself. So what you see with Intel is there are some SKUs, all pin compatible, that could be just standard host bridge SKUs that you would use for an Intel design, or you can see variants of this that actually have 2 Quick Assist units inside the PCH itself. So real estate-wise, this gives you the capabilities of actually having it all on the main board and not have to spread it out to multiple devices and having to use a bridge. This is all done internally. What's also interesting too is they've also added 10 gig capability directly from the Quick Assist unit, which then gives you the ability to do some more interesting things you'll see in a second. This Quick Assist that's in the PCH, as I mentioned, has 2 engines, and they say they can do 100 gigabits per second between compression and encryption. So here's going to be some scenarios of being able to use Quick Assist to actually locally apply this to a chassis perspective. The first one is let's just use the 7450 in the chassis as a gateway. So essentially, you take that 10 gig line, you bring it in, and you let this one board actually create a mechanism to decrypt data that's remotely accessible, that's coming in encrypted, and actually put it into the system so it's just used as an unencrypted sort of application space. This is probably the easiest way to go and add that kind of capability. Actually start to add some encryption. Let's say you don't want to go through and have everything in the backplane have to deal with encrypted data, so you can just use it as a gateway sort of functionality. This is a reasonable approach, but it's most likely not the approach most would take. Second approach is to go and actually just take the data coming in from the switch side and use it again as kind of an internal gateway. So the switch is the device that's actually moving it in at 40 gigabits per second, and it gets routed to this particular board. He processes it and then sends it out onto an unencrypted network. So you can have an encrypted network that's kind of a private network that brings the data in, and then the rest of the data can still be used unencrypted if that's what you want. Most likely, in my mind, I think the scenario is the final one where you're actually bringing in encrypted data. Everything is encrypted in the backplane, so the quick assist would be there to actually convert it into a form that the processors can actually use. And you may in turn decide, okay, some of this data will be encrypted and some isn't. So you maybe have a classified network and unclassified. So this is everything that's being handled inside the chassis and can be segmented out in either a classified or an unclassified type of network. Finally, why bother with all this? What we found is doing some internal benchmarking, looking at the OpenSSL protocol stack and software. We see, again, we were hoping to have some AES numbers, but we didn't have time to do that. Some other protocols that you can see here is an 8-time improvement in the performance, looking at a variety of different key sizes and packet sizes over what a standard algorithm would do within the processor itself. So we actually ran the benchmarks of looking at how this operated on the same board and how it looked with Quick Assist in line. And we saw an 8-time improvement with that. In the case of ECDH, which is another protocol, it was 10 times the improvement. So that's why we want to look at, if you really need to start to, and I think a lot of application, guys that are developing these applications are looking at encrypting this data and protecting it and locking it down on these boards. I mean, this is why you would want to use something like Quick Assist to do that.